he left off yesterday on self-normalized martingales.
Okay. So I'm going to start with something that I didn't finish last class. So the result that I'm going to talk about is we assume that the canonical assumption is satisfied. A and B are any random variables. Assuming that B is positive, I assume that this is true. And there are many examples, let me see. There are many examples that satisfy this property. Okay, I showed an example of a moving average. And so if we have an autoregressive process of this type, so we are looking at the yi equal to alpha yi minus 1 plus epsilon I, where epsilon I is normal, and normal 0, 1, and we are interested in estimating the parameter alpha. And so we are going to take the maximum likelihood estimation of this, of alpha, and then we will get bounds for its tail probability. So basically for the distance between the maximum likelihood estimator and alpha. Okay, so the log likelihood is given by this equation, so which is sort of standard. Then we can rewrite, if we equate to 0 and solve for alpha, we end up with this formula. And because of the definition of yj, we can replace yj by alpha, let me see, alpha yj minus 1 plus epsilon j. So that's how I end up from this step to here. So I have, then if I take the difference, I end up with this. Now, since the epsilon j's are independent, okay, so the epsilon j in this case is independent of all the yj minus 1 because of the structure of the process. Then this is a martingale. Okay, so this is a martingale, and well, it's a self-normalized martingale. The top is a martingale, but the bottom is the conditional variance. So this is the conditional variance. So I'm self-normalizing the martingale by its conditional variance, and I'm going to show you that this satisfies the canonical assumption. Okay, so the sum of the yj minus 1 square is exactly this. If I take, okay, since the variable epsilon j is normal with mean 0 and variance 1, this expectation is 1, and so this is exactly the conditional variance of the process of this. Well, no, the conditional variance of the martingale. Okay, so what we have is an is, so we have alpha hat is equal to minus alpha is equal to the martingale over its conditional variance. And it is, it is easy to see that the expectation of this quantity is less than or equal than 1. The way to see that, okay, is because of the form of if you expand this, you can see that everything comes together because this is normal 0, 1, because the epsilon j's are normal 0, 1, and it can be easily seen that this will be less than or equal than 1. Okay. So this canonical assumption is satisfied by the martingale and its quadratic variation. Okay. So the canonical assumption, so I introduced an example of the canonical assumption, and for the purpose of our studies, we assume that the lambda is real from takes values between minus infinity and infinity, or is non-negative, or it is in a range. And each one of these situations provide different types of inequalities. One thing that I want to point out, which is not in these slides, is that you can have here a function that is like lambda to the alpha, beta, b to the alpha, as opposed to just the squares. So that allows you to handle situations with heavy tails. But I'm not going to discuss that. You can find it in the paper, okay, which is with Glass and Lie. Now, okay, so we are going to use, if we assume that the conditional the assumption, if we assume this, then we can prove this is true for every real lambda. Then we can prove that this exponential inequality is satisfied. So this is satisfied by the autoregressive process, as I showed, but it's satisfied by Brownian motion, by continuous martingales, by discrete martingales under some definition of p square. Okay, so is the result clear? Is it what it is? So for all x and y, the probability that the a over b squared bigger than x and 1 over b squared less than y is less than or equal than e to the minus x squared over 2y. Now, I think this is a beautiful inequality. Okay, now, so the key step in proving this inequality is to keep the indicator when using Markov's inequality. So we have probability of a over b squared bigger than x, and then with intersection with s, which is any measurable set, then the probability is equal to the probability of e to the lambda a bigger than e to the lambda x b squared. Okay, I'm dividing by lambda over 2, so I'm raising this to the lambda over 2, and so I end up with this. And then the indicator that a over b squared bigger than x and s. And it's nice, you will see why this is important. So we can then complete the squares, okay, to make it look nice. And what we want to do is we want to use the canonical assumption. So if I use Cauchy-Schwarz, I can take this to the second moment, which gives me the canonical assumption bound. Okay, so I can take the expected value of e to the lambda of 2. Basically, if I square this, I get this. And so I have to take the square root, and then I have to take the expected value of the square of this quantity, which is exactly this. I'm not keeping the indicator here, it's an overkill. So then, any question?
The parenthesis is moved?
Excuse me?
The parenthesis is moved?
Oh yeah, it's important. An important thing is that the parentheses should be kept, because in the next slide you will see a slip of the mind. So
here? I think it's here.
no, the parenthesis is correct here.
I think no, but I think the parenthesis is oh, maybe not. Maybe okay.
Okay, good. That's a relief. Okay.
I mean, Bob is right. There's an open parenthesis there. There's no closed parenthesis.
Oh, another typo.
But those are typos. there's no issue as such.
Yes.
Here there are a single open and two closed, so they're missing open and closed parentheses.
Oh, okay.
But
Well,
nevertheless, there's no issue.
You have very sharp eye. I have. Well, thank you. You know, next time I will present it with the right parentheses. So thank you very much. Okay. So then this is less than or equal than 1. I'm sorry. This is less than or equal than 1 by the canonical assumption. And this, if we take lambda equal to x, this is going to be less than or equal, because this is going to be less than or equal than this, but the parenthesis in the previous slide was wrong. So the parenthesis should be here, and then by picking the maximizer is lambda equal to x. So by picking lambda equal to x, I end up with this. So I have x squared minus x squared over 2, the negative of that, and that gives me e to the expected value of e to the minus x squared b squared over 2 on this indicator. Okay. Now, so this inequality is unique to our paper. I haven't seen anything like this. The idea is that we are taking the expected value of the quadratic variation, or the conditional variance. If you have information about the distribution of your quadratic variation, then this will be better than the inequality that I advertised, because if I pick s to be 1 over the event 1 over b squared less than y, then this quantity is going to be bounded by I guess I'm getting lost. Okay. Well, then I can bound this by e to the minus x squared over 2y. Expected value of e to the minus x squared over 2y if I apply s to be that. So now let's apply this to the AR model. So we have that alpha hat minus alpha is equal to this quantity, and because of the inequality, remember we had okay. So what we have here is the result is for one side, but if we take the absolute value, then the result will turn out to have a 2 here. It's just by doing it in two sides. And so this tells me that if the conditional variance of your process is large, then the chance that alpha hat minus alpha is not large is small. Well, the chance that it is large is extremely small. So you can use this for testing a hypothesis. Okay? So on the set where the conditional variance is large, okay, the probability that this is large is going to be very, very small. Okay, so that's an example. And examples of self-normalized statistics will, so this inequality applies to Brownian motion. So the inequality again, so this applies to Brownian motion, to continuous martingales, and so forth. So what I'm doing is I'm giving you examples, and to this process. So suppose you have a sequence of variables that are adapted to an increasing sequence of sigma fields f sub I, and if we assume that the d sub i's are conditionally symmetric, then the expected the e to the lambda summation of d sub I minus lambda square summation of d sub I square over 2 is a super martingale, okay, which has mean less than or equal than 1. So this appears in a paper of mine in the Annals of Probability, and And the proof is not easy. You have to, it's tricky. You have to play with sigma fields and you know, this, as far as I know, is the first result dealing with variables without moments. So that is, I think that's the main contribution of to the theory. Aside from starting the self-normalization, the fact that you can deal with cases with infinite mean, infinite variance, so like Cauchy variables. So the inequality that I showed applies to sums of independent Cauchy variables. Another situation is if you have discrete variables, which are sub-martingale, so with conditional expectation d n b then f n minus 1, then there is this super martingale, and so you can apply it to this process, where an is the sum of these sub i's, and bn squared is this quantity. So you can apply it to discrete martingales and discrete submartingales under this definition of p sub n squared. Now, so those are the references. Now, can we take a 5-minute break?
Sure.
And then come back. So we'll finish early today. Okay, come back. So the title says that we are going to talk about sums of independent variables, okay? But at the end of this talk, I will show you about a new development in this direction, which is when you have an arbitrary stochastic process, okay? So you have a stochastic process. Let's assume that it is cat-lagged. You know, it can have jumps. And you want to get estimates of the expected time for that process to hit a boundary. It could be a two-sided boundary, but let us just look at this. So this is the stochastic process. Now, the typical way of dealing with boundary crossing is to assume that you know what the process is, okay? But so I started an approach which is different, and the approach is to use. So what we do is you're going to use. Suppose that you have n paths. Okay. Well, you look at the supremum. So what you do is you're going to take the supremums of these processes, and then you take the average. So what you do is you take. So I'm just telling you what the result will be, and it was motivated by what we did on this. So so if I call this the supremum, I going from 1 up to supremum for 0 less than s less than or equal than t of xs super I, okay? Then I take the sum of these and then take 1 over n. Now, this is a continuous process in S, okay? This is just, it's an of S. So it's a continuous process in S. And what I can do is I want to find bounds on the expected time for my process to reach B. And I will find it in terms of what I call A of t, which is equal to the expected supremum s less than or equal than t of xs, which in this case happens to be this average. So I'm using a historical approach to boundary crossing. I'm using, so if I have a simulator that gives me paths, like the motivation for this was global warming. So the question was, you see, in global warming, it's not possible to completely describe what the process is, but you can get projections, okay? So suppose that you have projections of your process, and you want to get information about the expected time to hit R on the basis of those projections. So I guess this is for the, if I have n processes, then this will be expected T R sub n. And this would be A sub n. Okay? So the result is, so this is a special case. This is for an empirical process. Okay? But so what I want to do is I want to find expected time to hit R of your process. And the result is that this expected value is bigger than or equal than the integral from 0 to 1 of A of R alpha T alpha R, A inverse of alpha R, d alpha. Now I have to explain to you what this means. So let us now look at the path. Okay, let us look at the, so I said that the AN of t or A of t is the expected supremum. So now we are looking at the path that is non-decreasing, and we are going to suppose that you have this expectation, which you can obtain by projections. Okay, so you're basing your decision on the projections. Now, then if I look at what this, so this is sort of like a mystifying thing. What that means is that I am going to look, so I have R here. And what I'm going to do is I'm going to look at the, so I'm going to filter the information about the hitting time for every value of R between 0 and R. So that's alpha R would be here. So I am basically capturing the information on the crossing of the process for the crossing for all R less than okay, for all R for all values between 0 and R. So okay, so this is an increasing process, increasing function. So I can invert it, and therefore I can look at its inverse. So I have A inverse of U. I have access to this function, okay, because I have an inverse. So in this case, what I pick is I'm taking the integral of A inverse of alpha R, so that I can capture all the information that my variables gives me about the boundary crossing, d sub alpha. Now, the interesting thing here is that in order to find a lower bound on the expected time to hit R, okay, all I need is to run my process up to time t. Okay, so I don't have to look into the future. all I'm doing is I'm using the past. Is that clear? So that was a surprise to me, but it just happens that if you don't have to go all the way to infinity to find a lower bound on the expected time to hit R. Okay? It depends on the paths, but you don't have to have all the information. You get a result with partial information, which is important because the models for the weather, you know, the global warming models, the models that predict the temperature are, you know, there's a price to run them. So you don't want something that goes, that is beyond your budget. So this was an important condition. And so then, so this is the bound. Now, if the process is Brownian motion, okay, then the A of t, so I'm going to give you an example of a process. So A of t is going to be equal to the expected supremum s less than or equal than t of ws, which is going to be the square root of t times the expected value of the sup s less than or equal than 1. Let me see, w1. Let's look at the absolute value of the process, but that's not necessary, in which case I have this, okay? So this number, this is a fixed number related to pi because of the, we have like a, the supremum of a Gaussian process up to 1. So, but the growth rate is the square root of t. So A of t for Brownian motion will satisfy this property. It will be a trend of the square root of t. And we know what the constant is. So, you know, so you can apply this method to any stochastic process for which you know what the expected supremum is. And by using empirical processes, using empirical paths, you can get a lower bound. That's a special case. Okay, so now I use this method in a study on forecasting at the a drought in California. So the typical estimators that geophysicists use were not as good as this one. Okay, so I published a paper on the drought, and okay, so and I'm hoping that I can use this to get a lower bound on the time that the global warming hits a point of no return, as they say. So, you know, for a politician who is a denier of global warming, it's important to find out, if they find out that the time to hit global warming, point of no return, won't happen on the average before something, then they can say, oh, we don't have to worry yet. Okay, is that clear? So I'm thinking of selling this to a politician. Now, under some conditions, I can also get an upper bound. Okay, I need to assume that I have control over the growth of the process, and this bound is sharp. That is to say, there's a stochastic process that satisfies this property. So anyways, so that's sort of like a motivation for going through all this algebra. Okay, so I stole the
Clicker.
clicker. Oh, maybe I have it here. No, I have this here. Well, I can point.
Oh, okay.
Oh, here. No. You mean I am a magician. Who took it? Oh, okay, here it is.
Oh,
Abracadabra. Okay. So we continue. Okay, so basically, you know, I work at Columbia, and one of the reasons why they hired me is because I work on Wald's equation. So because Wald was the founder of the department. So anyways, so I'm going to show you some new results on Wald's equation. So suppose that you have a sequence of IID variables adapted to the sigma field of the variables, and I assume that the variables have mean nu, and t is a stopping time adapted to sigma of x sub I. If we let Sn to be the sum of the x sub i's, then expected value of St is equal to nu expected t, whenever expected t is finite. This is what is known as Wald's first equation, and if the mean is 0, then expected value of x1 square is fine, and expected value of x1 square is finite, then you have this. Now, this result is the beginning of the theory of sequential analysis, which has a very interesting history, because the reason why he worked on this was because of life and death situation. So Wald was approached by a general in the army that was concerned. He wanted to provide the soldiers a high quality bullet. Okay, so he wanted to provide them with high quality bullets so that when they use the rifle, if it misfired, they should try again. Then the idea is that the bullets are of such high quality that you shouldn't trust the rifle. So you throw away, get another one. Okay? So the way at the time, the way that people could check a bullet batch was by taking a random sample of size n and then firing it, and then on the basis of that they had an idea as to whether or not but he wanted really high quality bullets, and that, you know, by the time he could, the sample size then had to be very high, and so he almost didn't have any bullets. So it was, you know, it was self-defeating, because you managed to get high bullets, but there are only a few left. So Wald then, thinking about that problem, created the sequential approach to testing. So originally the approach to testing was you take a sample of IID variables and you control the type 1 error and the type 2 error, okay? But if you wanted the type 1 error to be very small, you had to have an appropriate sample size. So what he did is, if there is overwhelming evidence, so you start sampling, and when you find overwhelming evidence that the bullets are good, That is to say, if you start firing and the, the curve. So he devised a walled curve. Suppose that, so he said, so here is the way the process goes. So there are some bullets that misfire, but if I keep on going this way, so sometimes the bullet fired, sometimes it didn't misfire. So it's flat when it doesn't fire. Now, he created a curve based on the use of Wald's equation, a curve, and he said we are going to stop taking samples when the process reaches the boundary. And he used Wald's equation to calculate the type 1 error and the type 2 error of the process. So that's how it was done.
Was there two boundaries?
Excuse me?
Was there two boundaries?
Well, in this case, every time you they are curved boundaries. Yes, what was the question again?
Two boundaries?
Oh, well, in this case, the example that we're doing is for processes that are growing. So it's only one boundary. But it could be for two boundaries.
But you have two decisions, right?
Well, if it didn't happen, okay, by that time you finish your bullets. But with high probability, the process will hit the boundary. Okay? So yeah, you have two decisions. If by time n the thing hasn't crossed the boundary, then you continue until it hits the boundary. Because that when it hits the boundary, there's a certain guarantee that the quality is good. You might start sampling, and by luck, you get bad bullets initially, but you don't stop necessarily there, because that was just by chance. So that created a new area of statistics, which is known as sequential analysis, which is very important these days, especially in medical statistics. Okay, so now, so this is Wald's equation. And as I would show you, it is important to extend Wald's equation to the case when the mean is not zero. And so I would show you how to extend it. Now, if the mean is not zero, you can write a formula, but it's not something that you can compute. Okay? So you can extend the formula and get an expression, but if you want to be a useful expression, something that you can compute, what you do is you use decoupling. So this is sort of a continuation of the lecture on decoupling. So where does decoupling come from? So basically, what you have is a new perspective to Wald's equation. Okay, so a new way of viewing Wald's equation, which is very useful. So what you have is you have x sub I, again. In this case, I don't assume that they are IID, it's just independent. Then Wald's first equation is telling me, suppose that the variables don't have mean zero. Then it is telling me that this will be equal to the sum of the expected values of xi. Well, let's assume that they are ID for a second. So this is going to be what? Who remembers Wald's equation? Bright students, brilliant. This is equal to new expected value of t, okay? Now, I can, if I take an independent copy, x sub I tilde, with the same distribution as this one, then by the fact that they have the same distribution, this will be equal to, well, because the mean is new, this is expected value of x1 times the expected value of t, but all the x's have the same mean as the x tildes because they have the same distribution. So I can write this as expected of x1 tilde times expected value of t. And then so then I can play the game backwards. So this is also equal, you know, by Walt's equation, it also holds that this is equal to the expected value of the sum I going from 1 up to t of x sub I tilde. Right? Okay. In this case, the x sub I tildes are independent of the stopping time, so you use Fubini's theorem. Now, suppose, so now I'm going to look at this at the second moment. So this is a rewriting of Walt's equation. The second moment, so what I would show you is that the expected value of st squared is less than or equal than twice expected st tilde square. Now, it's interesting because here you are, so, okay, let's look at this one, So expected st is equal to expected st tilde. Now, you know, it's been a long group of lectures. Have I ever spoken about this before? No? Good. You know, I have spoken to a lot of people, so I just don't want to bore you. Okay, so you could use this, you know, abstractly as an idea. You know, suppose that you have a sum of IID variables, and you want to stop at the time that the sum reaches a boundary. Okay? Then what you can do is you ask your friend to do the same thing. So you have your friend is in the moon, and he cannot, you know, he's not an expert on the process. But so what you tell him is, so you are going to use your experiment, and he will tell you stop now. Okay? So the person has the outcome of your experiment, and then he'll tell you stop now. And then on the average, they will get the same answer. They will stop at the same time. Any questions? Yes?
So is one of them easier to compute, and you're using that to get, is it like an alternate proof of Walt's lemma?
Well, it's a rewriting of Walt's lemma. But the reason why it's important is because Walt's lemma works with real valued variables. But if you want to extend Walt's equation to matrices, the sum of matrices, or Banach space valued variables, then by using this heuristic, this approach, you can get bounds on the expected time for you know, the determinant of sum of matrices reaching a boundary. So that's okay. So now, in terms of so what I have is, what I'm going to show you is that you can have this result. Now, so by using an analogous argument, I can also say that expected of st squared is equal to expected s tilde t squared.
So is there an extra 2 there, or a missing 2 there?
Excuse me?
Is there a...
This is mean zero, that's what you do.
Oh, okay.
Yeah, so this is for mean zero. It's Walt's equation for mean zero, and this is for non-mean zero. In Walt's equation, typically you assume that they are IID, but in this case they can be any independent variables, as long as they have finite mean and finite variance. And okay. Okay, so now I want to point out that you can study this when you study the process S tilde t. That has has the same distribution as S t tilde, where what I do is I'm going to stop. This is where my friend stops when I tell him or her, and this is when I stop when my friend tells me. Okay, so they are equivalent, and this will be helpful for the understanding of the result. Okay, so the result that I'm going to prove, I said, is that the expected value of st squared less than or equal than 2 expected s tilde t squared. And this result is sharp in that there are a sequence of variables and a stopping time where asymptotically they reach the value of 2. Okay. So to prove this, I have a series of lemmas. So the first lemma is that suppose that I have variables with mean nu sub I and variance sigma sub I square. Then the expected value of st tilde, which is the same as this expectation, st tilde square, is going to be equal to the expected value of the sum. You remember, I can play with t or t tilde. Okay, so this result, okay, yeah. So what I can do, if I can play with this and write this as the expected value sum I going from 1 up to n of sigma sub I square to the t, plus the expected value of the sum I going from 1 up to t of nu sub I square. That's the result that I'm aiming to prove. And the proof is the following. So I take expected st tilde square and I can rewrite it in this way. I add and subtract and add the means. Then I square. And I noticed that since t is since the t and xi's are in t tilde and xi's are independent, this expectation is 0, because when you condition on t, you have something that has mean 0. So I have this. So therefore, the result is expected s tilde t square is equal to the expected value of the sum of the variances at up to t and the expected value of the sum of the means up to t tilde. Now, so let's keep that result in mind. Okay, and the proof is now a few lines again. Okay, so I could make it more complicated if you want. It took me a long time to come up with it, but it turned out to be easy. So you can, now there's another lemma which says that the expected sum of nu sub I square is equal to this, where I add and subtract. When I add and subtract st and then square, so I add and subtract st and then square, I get this. Okay? Now, here, this is not mean zero, because I have the same variables, the same stopping time. So what I do is I use Chebyshev's inequality. So this is going to be less than or equal than the expected of st square to the square root of that times the expected value of this square, the square root of that. And this is just the expected value of the variances. So so this is exactly equal to this, or bounded by this. Okay? So then what I notice is that the expected of st square, so this is one part, and the other part is I am regarding expected of st square and finding a bound on it. So the first bound is on the expected of the sum I going from 1 up to t of nu sub I. The second bound is on expected of st square. And you know, these are the corresponding bounds. Then I put them together. So using inequalities 7 and 5, we are going to get that expected of st square is this less than this, and then which is, if you square this, you get the expected of nu sub I square, the sum of the nu sub i's up to t square, plus the expected sum of the sigma sub I square, right? And now we had a bound on this, on the first one. Okay? So that is bounded by this quantity. So then putting them together, I end up, and if I square, then I get this bound. And that's the end of the result. So this is a result with an expert in sequential analysis. He wrote a book on sequential analysis, and he's the one who posed the question. Now, another result is if you have non-negative variables, then you can get the lower bound with a constant of 1 over 5. But the proof is more complicated. And this constant is also sharp. So there's a lower, an upper and lower bound when they are non-negative. Now, okay, so now let me go to the application. So let's define, so this goes back to the original. Why did I come up with the result that I put here once I got this? So if I define A sub n to be the expected maximum of Sj square, then I can see, you know, I have the, if I want to look at the first time that the square hits the boundary, okay, that is obviously going to be bigger than or equal than R. So then I use the decoupling argument, and I get less than or equal than twice expected S sub tilde square of TR. And this is less than or equal than the expected value of the maximum, okay, up to TR. Therefore, I have this quantity is A of TR, because I first integrate with respect to the x's and then integrate with respect to t. So this is bigger than or equal than R if and only if expected A of TR bigger than R over 2. So this gives me a lower bound on the expected value of a function of the stopping time t sub R. Which motivated me to work on arbitrary processes, boundary crossing by arbitrary processes. Okay? So let us assume that we have an arbitrary process. So if we have an arbitrary process, non-negative measurable, okay, let's assume it's non-negative measurable, okay? Then the expected value of the supremum, if I define that as A of t, and t sub r is the first time that xt is bigger than r, then for such that, so I have this inequality. This is bigger than or equal than r over 2, like in the case of sums of independent variables. Now, if in addition A of t is assumed to be concave, in this case it's a continuous process, so I can use concave. If the function A of little t is assumed to be concave, then I can find the inverse, concave increasing, then I can find the inverse, okay? And I can take this expectation inside. So I have expected t sub r bigger than or equal than A inverse of r over 2. So this is a special case of the result that I discussed earlier, that has applications to global warming. Okay, now if A is continuous and strictly increasing, okay, there is a sharp inequality for any Cadillac process. So if this expectation is continuous and strictly increasing, then what we have is for any g non-decreasing, you know, like any power or any convex function or whatever function you want, which is non-decreasing, the expected value of g of t sub r is going to be bigger than or equal than the integral from 0 to 1 of g of a minus 1, a to the minus 1 r alpha d alpha. So that's, you know, that's the end. Oh, well, not quite. So Hitchenko, who's a Polish mathematician, when he saw our result, he was able to extend the upper bound was able to extend it to the case of p bigger than 1. But he had to assume that the variables were non-negative. And this result can also be extended to the case of arbitrary variables. So this result applies also if you have arbitrary variables that are non-negative, where this is your sum and this is the decoupled sum. So decoupling, so my work on decoupling led me to deal with boundary crossing. Question? Okay, and that's the end. Okay? Now, so I'm currently working on an extension of this to arbitrary variables. Not only a sum of independent variables. And Siva is going to help me. Okay, thank you. Okay, so
we end early